Hello, welcome back. In this exercise we're going to use the normal distribution to approximate binomial probability. So this is going to be a little bit tricky because we're using a continuous probability distribution to estimate discrete probabilities. So as you'll see as we go through the exercise, we have to incorporate what is called the continuity correction factor or continuity factor. Because we're using this continuous distribution to estimate a discrete probability. So it sounds tedious, but it's really not that bad when you see how we do it. Just small little tweaks to our numbers. So here we go. An interesting survey I found not too long ago looking at gun ownership in the US. So here we have number of guns per capita is on the rise. We have more guns than we have people, roughly just under 113 guns per 100 residents. However, the number of households with at least one gun has declined. So we have more guns and fewer homes, and it's declined to roughly 1 in 3. So let's consider a group of 300 homes to answer these questions. So we're using here our continuous normal distribution. Can we use a normal distribution in this case to estimate these binomial probabilities? Well, as long as it satisfies these two conditions, that the sample size times the probability and the sample size times 1 minus the probability are greater than 5, then we're okay to approximate these binomial probabilities with the normal distribution. So if my sample size is 300 and my probability 1 in 3, so let's just call that 0.33. So this is going to be equal to 100, so that checks out, we're okay there. And same here, this is 300 times 1 minus 0.33, so that'll be roughly 200, so yeah, that checks out there. So our sample size is sufficiently large that we can approximate these binomial probabilities safely enough with the normal distribution. So let's get into our first problem. What is the expected number of households that own at least one gun? We'll actually also need to get the standard deviation in here too, so we'll get that because we need the parameters of our normal distribution that we're going to use. So our expected number, so our mu, our average number of households, this is just n times p. We have just actually calculated that, 300 times 0.33, so our expected number, our average number of households in this 300 homes that we're considering would be 100 of those homes we would expect to hold a gun, at least one gun. Our standard deviation, so this is the square root of np times 1 minus p. So this will be 300 times 0.33 times 1 minus 0.33. So this is going to be, let's get the calculator out here, 300 times 0.33 times that'll be 0.67 equals square root, so about 8.14. Okay, so now we have the parameters of our distribution. Now we can go ahead and calculate some of these probabilities. Now, keep in mind that anytime we're using a normally distributed variable, we are also working with the standard normal distribution with 0 mean and standard deviation of 1. Now, I'm going to try not to get this too messy here. I just want to remind you we're always working with these two distributions simultaneously. Okay, so part A, we're done. We've got we have our expected value is 100 and we have our standard deviation was 814. So part B, what is the probability that 90 or fewer own a gun? So here we're looking at some value 90 or fewer. Now this is where this continuity correction comes in. Because remember, if we look at in a continuous distribution, the probability that x is equal to any number. So let's say x is equal to 90. From a continuous distribution, this would be always 0. From a discrete distribution, however, we could calculate precisely that probability. So what we need to do in this case, we want to include exactly 90 or fewer. So we want the probability that it's exactly 90 or less. So we have to ensure that our calculation includes the 90. Otherwise, it's not going to be it won't be a fair estimate. So for that reason, we include the correction factor, and we'll just add 0.5. We'll add 0.5 to that 90. That way, when we calculate our probability, it will be a fair approximation of the binomial probability. So all we need to do in this case is we'll look up the probability that x is less than or equal to 90.5. So we need to figure out what is the corresponding z value. So z, this is using the same formula that we've been using in other videos on this topic. X, our value of interest, is 90.5. Mu is 100. And our standard deviation is 8.14. So now this gives us a value, let's see, 90.5 minus 100 divided by 814. So let's call that 117, negative 117. So here's negative 117. And so that probability that they own 90 of those households or fewer own a gun, that would be this area to the left. And so if we pull up our tables, I'm looking up negative 117. So here's negative 1.17, right? This z is negative 117. Here I've got first that negative 1.1, and then here's that second decimal, 0.07. And where those come together, I have a value of 1210. So that area there, 0.1210. So that's the probability equal to, let's say, about 12% chance that 90 or fewer own a gun. There we go. That's all there is to it. Part C. What is the probability that between 85 and 115 own a gun? Okay, so let's get rid of all of this nonsense. So now I'm looking at between 85 and 115. So again, I want to include those endpoints, 85 and 115. So I'm going to include a correction factor here. This will be 84.5 because I want to include 85, which is over here somewhere. And 115, well, I want to include 115, so I'm going to correct this up to 115.5. And now I want to figure out that probability between the area under the curve between those two values. So we need both z-scores here. So the first one, I'll get 115.5 minus 100 over 8.14, and that'll give us that upper z-score. The lower one will be 84.5 minus 100 over 814. That'll give us the lower of the two. Let me find my calculator. So 115.5 minus 100 divided by 814, 1.9. And the lower one, 84.5 minus 100 divided by 814, negative 1.9. There we go. Negative 1.9. These are both exactly 15 away from, well, 15.5 away from away from our average. So we get an absolute value, we have exactly the same numbers. Now, for our probabilities, what we're going to do, well, first find, actually there's a couple of ways we could get this one. We could cheat, take a shortcut. Let's do it the long way. You can figure out the shortcut way on your own. So here we'll have the first one for 1.9. So we're right in here. I'm kind of squeezing this in. I'm running out of space there. So when we look at the probability for that one, that will give us this whole area to the left. But then what we'll need to do, all we want is this piece in the middle between here and here. So we'll have to then figure out the probability that corresponds to negative 1.9 and subtract that away, leaving us only that range, that probability of interest. So let's first look up positive 1.9. Oops, that's not what I want. My Z table. Positive 1.9 is, there's 1.90, so it's 0.9713. 0.9713. This one here, negative 190, it's 0.0287. Okay, so the area between those two, so my probability of having that Z less than or equal to 1.9 or greater than or equal to negative 1.9, which is the same as saying the probability of an X less than or equal to 115 and less than or equal to 85 is 0.9713 minus 0.0287, which gives us 0.9713 minus 0.0287, oops, equals 9426. 0.94, so a pretty high probability that between 85 and 115 of those individuals own a gun. Now, what is the probability that 115 or more own a gun? So now we're looking up, just up in this area here, but again, I want to include that 115 in the calculation. And so I need to make sure, I'm looking at the upper tail now, the right-hand side of this distribution. So now I want to include that 115. So I want to correct this downwards to 114.5. And now I'll include that 115 in the calculated probabilities. So let's clean this up a little bit. So now I'm going to be looking up the Z that corresponds to 114.5. 114.5 from 100 out of 8.14. So this is equal to 114.5, oops, 114.5 minus 100. Divided by 814, 178. So that's down here now. This is 1.78. I don't need any of this stuff anymore. And now we're looking at this area here, that upper tail. All right, I want 115 or more. So now we have two ways that we can do this. One is that if I look at the Z tables, these are always giving me a lower tail probabilities, right? We always have the lower tail probabilities here. We always have the lower tail probabilities here. What I want is the upper tail. So in order to get the upper tail, I'd either have to do 1 minus this piece, this whole shaded region here, and that would give me the upper tail probability. Or I can take advantage of the fact that this distribution is perfectly symmetric. So if I have this z here, let me clean this up. If I have this z here, if these two z's are exactly the same in absolute value, in magnitude, then this area will be exactly equal to this area. So if I have a test statistic, in this case, that value is 1.78. So let's just look up 178. And so 178 is right here's 1.78, and those come together, I'm right here, 0.9625. So that gives me an area here of 9625. If what I want is out here, then I need to calculate 1 minus this, and 1 minus 0.9625 is 0.0375. So there's my answer for the problem, 0.0375. It's a probability that 115 or more own a gun. Now, we can also look at this the other way using the symmetry of this distribution. If I look up negative 1.78, so if I come over here and if I look up negative 1.78, let's clean this up a little bit. There's negative 1.78, and where those come together, there we go, 0.0375. Exactly the same answer. So we can do this either way. If we're comfortable with the symmetry of the distribution, we can just take that, use that to our advantage and skip this little step. But it's a small little step, so maybe it doesn't matter to skip it. It's not worth the risk of a silly mistake. So hopefully that helps. These normal approximations, the only thing that is usually a real challenge or kind of annoyance more than anything is these continuity correction factors. But once you get the hang of that, it shouldn't be a problem. So hopefully this was helpful. I hope you'll continue to watch more and more of these videos. Thanks for watching. Bye-bye.